Let's look at the solution of number system bytes. Question 1. X is the set of the first 100 natural numbers. How many elements are there in X such that when they are divided by 7 and 8, they give different quotients? Okay. Now see, because we are looking upon division by 7 and 8, what would be the possible quotients up until 100? Up until 100, possible quotients where 7 and 8 give me the same quotient would lie in the range 0 to 12 only, because the highest multiple of 8 under 100 is 96 and it can go up till there to there. So let's say quotient 0 in both these cases would be numbers 1, 2, 3, 4, 5, 6. 7 would not work because when 7 itself is divided by 7, quotient is 1. When it is divided by 8, quotient is 0. So when quotient is 0, we get these 6 cases. Quotient is 0 as in for each of these 6 cases, if you divide by 7 or you divide by 8, the quotient is going to be 0. Okay. When quotient is 1, the numbers would be 8, 9, 10, 11, 12, and 13. We can't go beyond this because 14 upon division by 17 gives a quotient of 2, but upon division by 8 gives a quotient of 2 here. Upon division by 8, it will still give a quotient of 1. So let's go quotient of 2. With quotient of 2, it will start off with 16, 17, 18, 19, and 20. Because 21 onwards, again, it would be a problem. Upon division by 7, you will get a quotient of 3. Upon division by 8, you will get a quotient of 2 only. With a quotient of 3, it will be 24, 25, 26, 27, 28 onwards. Does it work? Quotient of 4, you would get 32, 33, and 34. Not beyond this. Can you see what I've tried to do here? What I've tried to do here is the starting point is multiple of 8. The ending point is just before multiple of 7. Multiple of 8 just before multiple of 7. Multiple of 8 just before multiple of 7. Multiple of 8 just before multiple of 7. Quotient equal to 5, I get 40 and 41. And quotient equal to 6. The only number that fits this category is 48. After this, quotient with when we reach the next multiple of it, see, ideally the series that is getting created is this, all multiples of it. The problem is you're only considering natural numbers, so 0 is not in consideration. So we count it this way. How many numbers do we get? 6 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. So sum of first 7 natural numbers. So 27. These for these 27 numbers. Upon division by 7 or 8, you get the same quotient. So out of first 100, when you remove these 27, answer to the question should be 73. Next, if ft is equal to 2 raised to power p plus p square, where p is a prime number, what is the number of possible values of p for which ft will be prime? Okay. Fun thing. All prime numbers of this world can be represented as 6k plus minus 1, except 2 and 3. So let us try with 2. 2 raised to the power 2 plus 2 raised to the power 2. It will be an even number apart from 2. So this will not be prime. 2 raised power 3 plus 3 raised power 2 gives me 8 plus 9, which is equal to 17. So yes, this is a prime number. Next, 2 raised to the power 6k plus minus 1 plus 6k plus minus 1 raised to the power 2. Now see, 2 here raised to an odd power hoga. 2 raised to an odd power hoga hamesha. So what I am looking at here is remainder with 3. Minus 1 raised to an odd power, the first number, I am looking at remainder with 3. Minus 1 raised to an odd power will always give me a minus 1. And whatever it is, 6k plus 1 or 6k minus 1, when I square it up, I will definitely get a 3k plus 1 or remainder of 1 with 3. Can you see this result will always be a multiple of 3? And because it is always a multiple of 3, it will not be a prime number. So how many distinct values of p can be taken? There is just one value of p that is acceptable, and that is 3. Next, if x is equal to blah 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 and y is equal to blah blah blah, then which of the following statements is true? One leading guide in life that I can give you when it comes to identifying prime numbers and composite numbers, you can only check if it is a prime number if it's a small number. Can you see this is a huge number? This is a huge number because if it is a very huge number and you're expected to check if they are prime or composite, the rule of thumb is it will be composite. Because in order to confirm whether a number is prime or not, you have to go up until the square root and then check and then divide it by all primes under it to see if the original number is prime or not. Of course, you're not expected to do that in an intelligence exam. But for those of us who know who want solution, so let us do that. Here, can you see, if I take out 20 raised power 4 common, I'll get 20 plus 1 plus 20 plus 1. So I get 20 raised power 4 plus 1 into 21. This is x. So x is definitely composite. This is definitely composite. Okay. So what I'm doing is 16 raised to the power 8 minus 1 minus 16 cube 16 square plus 1. Yes, I can break this down as 16 raised to the power 4 plus 1 into 16 square plus 1, 16 square minus 1 minus 16, 16 square plus 1. I can take this portions out. I'll get 16 square plus 1 into 16 raised power 4 plus 1, 16 square minus 1 minus 16. This is why I have identified two factors which are non-ones. So this is also a composite number, or the guiding light was good enough for us to mark these straight away under 10 seconds and move on. The sum of digits of a 4-digit number is 34. What fraction of such numbers are divisible by 11? Okay. Sum of digits of a 4-digit number is 34. Okay. Let's see. The 4-digit number that you have A, B, C, D. A, B, C, D. Can you see that you need at least you need at least 2 nines? You need at least 2 nines because even if you were to deal with very small numbers, if you had 0 nines for the 4-digit number, if you had 0 nines, would you reach a summation of 34? No, it is impossible. You need to have at least 2 nines involved, at least 2 nines. And when you have 2 nines involved, the other 2 need to be 2 8s. You can have, or basically for 34 as a sum, you can have 9 9 8 8. This is the smallest case possible where you have minimum number of nines. Next case you can go down is 9 9 8 7. Sorry, not 8 7. Oh, 9988, 9997. These are the only two possibilities. These are the only two possibilities. Okay, if these are the only two possibilities, how many cases do I have here? It will be 462 or 4 factorial by 2 factorial, 2 factorial. 24 divided by 4. So 6 cases here. And how many cases will I get here? 4 cases here. So altogether, there are 10 such numbers. There are 10 4-digit numbers whose sum of digits is 34. Now, what fraction of these numbers are divisible by 11? What fraction of these numbers are divisible by 11? See, none of the cases here will be divisible by 11. That is guaranteed. None of the cases here will be divisible by 11. Here you can potentially have 9, 8, 8, 9. This would be divisible by 11. 8, 9, 9, 8. You could have 8, 8, 9, 9, and 9, 9, 8, 8. These are the 4 numbers that will be divisible by 11. So overall, the answer to the question will be option D. Out of 10 possible numbers, there are 4 numbers which can be divisible by 11. I hope I am not missing out on any case. Yes, these should be all. These should be all. Answer to the question should be option D. Last, if x, y, z are natural numbers such that x is less than y is less than z, and 1 by x plus 1 by y plus 1 by z is equal to 1, how many values can y take? Wonderful. X is less than y is less than z, and 1 by x plus 1 by y plus 1 by z is equal to 1. So see people, fun thing. If x was 1, can you see it would be a problem? If x was 1, this fraction here itself would be equal to 1. And then 1 by y and 1 by z would exceed it. So x cannot be 1. X cannot be 1. Let's say if x was 3. Let's say if x was 3. So I would have the largest possible value of 1 by x plus 1 by y plus 1 by z would be 1 by 3 plus 1 by 4 plus 1 by 5. If I add these 3 up, how much do I get? 60. So I get 20 plus 15 plus 12, which is equal to 47 by 60. 1 by 3 plus 1 by 4 plus 1 by 5. Even this doesn't reach 1. Even this doesn't reach 1. So can you see, if I go down the path of 1 by 4 plus 1 by 5 plus 1 by 6, 1 by 4, 1 by 5 is same. I have effectively reduced 1 by 3 to 1 by 6. The value would go down. I will not reach any value. I will not reach 1 if I take x as 3 either. So this is also unacceptable. Let me get rid of this working at the bottom. Now that I've gotten rid of this also, now I know x has to be equal to 2. The only possibility, the only case that is acceptable is x equal to 2. So now I have 1 by y plus 1 by z is equal to 1 by 2. Now checking, if y was equal to 4, if y was equal to 4, can you see 1 by 4 plus 1 by 5 is equal to 9 by 20, which is less than half. Even if I went ahead and checked other values or other cases for y, 1 by 5 plus 1 by 6, can you see the value will fall only because 1 by 4 has been replaced by 1 by 6, which would mean y cannot take value of 4. Y has to be greater than 2 and y cannot take value of 4 or higher. So the only acceptable case is y is equal to 3. And if y is equal to 3, the only acceptable case that comes out is z is equal to 6. The only case that works is 1 by 2 plus 1 by 3 plus 1 by 6. The question is, how many values can y take? The answer to the question is 1. The only acceptable value that y can take is 3. that concludes this week of number systems by number system bytes. Hopefully you learned something throughout the week and during this video. That will be all. Okay, bye.